Today we're going to transition from electricity, which we did before our break, to magnetism. You're going to find that there's a lot of similarities between electricity and magnetism, just like there was between gravity and electricity. Just keep in mind throughout the whole unit when we talk about north poles and south poles and so on, that we're not talking about positive charges and negative charges. They're not the same thing, but there are a lot of similarities. First thing we're going to do to talk about magnetism is define a new term called the magnetic domain. Domain is a tiny little region, this microscopic region inside a ferromagnetic material, we'll talk about that in a second, that are represented by arrows. What's a ferromagnetic material? The ferromagnetic material is a material that has the potential to become magnetized. It's not magnetized right now, but it can become magnetized. An example of that would be steel. The legs of your desk are made out of steel. They're not magnets right now, but if you bring a magnet nearby, you can cause the legs of those of your desk temporarily become magnetized because it's a ferromagnetic material. It has the ability, the potential to become magnetized. Now, if you look at a ferromagnetic material under a microscope, you're not going to see a whole bunch of little arrows. In fact, you're not going to see anything that is going to tell you that it's ferromagnetic or magnetic or whatever. If you could magnify it enough, you would see electrons spinning, electrons rotating. And patterns of electron spins would give you domains. Now, we can't draw electron spins and commonalities and patterns of electron spins. So what we're going to do is simply represent similar patterns of electron spins with arrows. Each little region with these little similarities of electron spins is a domain that we're going to represent by an arrow. If you have that piece of steel or iron or cobalt, some ferromagnetic material, and we represent these domains by arrows, what we would find is that normally these arrows would point in more or less random directions. This is a non-magnetized ferromagnetic material. This is the leg of your desk right now. To become a magnet, we have to cause those domains, those regions that are represented by arrows, to point in similar directions. So instead of pointing in random directions that we have right here, we have to get these domains pointing in more or less, at least, the same direction. Something like this. Now, how do we get them to point in the same direction? Well, there's a couple of ways that we can do that. One way is to bring another magnet nearby. Here's a permanent magnet. This permanent magnet has the domains aligned in it already. Those domains in the green one, the permanent one, that we bring nearby the non-magnetized ferromagnetic material, have an influence on this desk leg or whatever other piece of steel or iron or whatever it is that's ferromagnetic. The influence that they have is to cause these domains that we're pointing in more or less random directions to start aligning in the same directions that these domains are aligned in. So what we've done here is temporarily made this non-magnetized ferromagnetic material into a magnet. It's temporary. We take this other magnet away, and this will eventually go back to being random, pointing in random directions. Okay? But for the time being, as we bring this nearby, and even for a little bit of residual time afterwards, it's going to remain magnetized. That's one way that we can cause the domains to become aligned. One way that we can turn this non-magnetized ferromagnetic material into a magnet. The other way, you guys have probably seen this before in grade 4 or grade 5 or whenever you look at magnetism for the first time. If you wrap a wire around it and you apply an electric current through that wire, then you're going to cause these domains to become aligned as well. Okay, what happens is that the wire generates a magnetic field, and that magnetic field causes the domains inside this ferromagnetic material to start pointing in the same direction. We'll talk more about that tomorrow. Okay, for now, just trust me on that. Okay. Number one, you can bring another magnet nearby to align the domains. Number two, you can apply an electric current, not through the ferromagnetic material, but to a wire that's wrapped around the ferromagnetic material. In either case, you're going to cause these domains to become aligned. This is an electromagnet, right? Yeah, how many people in elementary school when they were, whatever grade it was, built those little electromagnets where you wrap a wire around a nail attached to a battery and try to pick up thumbtacks? How many people did that? Okay, 2 of you? 3? Okay. Most of you guys were deprived, I guess. That's the fun thing. One of the fun things you do in elementary school is make the little electromagnets that pick up the thumbtacks. Anyways, if you didn't do it in grade 4 or grade 5, pretend you did. Okay? You can picture at least what I'm talking about, right? Wrap the wire around, attach to the battery, pick up the little thumbtacks, because you're temporarily aligning the domains inside that steel nail, this ferromagnetic material. By the way, before I flip the page, let's go to that word again. Ferromagnetic. Ferromagnetic. Where have you seen the term ferro before? I'll give you a hint. Sometimes you see ferro abbreviated Fe. Where have you seen the term ferro before? Yeah, it's the Latin for iron. Okay, that's where the term ferromagnetic comes from. Iron is the most commonly known ferromagnetic material. So the symbol that we give to iron is Fe, ferrous, ferro, right, from the Latin, same Latin base. Make sense? All right, let's start drawing connections now between electricity and magnetism. Not so much one thing affecting the other, but at least similarities between electricity and magnetism. Talked about 3 laws of electricity. We're going to talk about 3 laws of magnetism as well. As we do, remember what I said at the beginning of the lesson here. Poles are not charges. Charges are not poles. But if like charges repel each other, then like poles will repel each other as well. Positive repels positive, well, north repels north. North isn't positive, but positives repel positives and norths repel norths. And south repels south, of course. Next one. You guys can probably figure out the next one yourselves here. Right? If like poles repel each other and unlike charges attract, then unlike poles of a magnet will attract each other as well. North attracts south, and south attracts north. And finally, the third one, you guys remember way back now, charged objects attract neutral objects. We can't talk about charges here. We're talking about poles. So north poles and south poles will attract, we can't talk about neutral objects now either. Well, poles will attract, what's the equivalent of a neutral object? Yeah, a non-magnetized ferromagnetic material. North and south poles of a magnet attract non-magnetized ferromagnetic materials. This is an important word here, ferromagnetic materials. It is because north poles and south poles don't attract pieces of paper or pieces of wood or pieces of plastic. They don't just attract non-magnetized things. They attract non-magnetized ferromagnetic things. And why? Well, it's essentially because the domains in the magnet, in the one that's already magnetized, temporarily aligns the domains in the non-magnetized ferromagnetic material. So for instance, you got your non-magnetized thing right here with domains pointing in random directions. You bring the magnet nearby that has the domains aligned like this. That causes the domains in this one to temporarily align like this. I don't know if you guys remember this, but when we talked about electric fields, if the electric fields joined up, then it meant attraction. If they were pushed away from each other, repelled each other, then it meant repulsion. Well, these domains, if we extended them, would join up, right? So that means we have a force of attraction here. Magnets will attract non-magnetized ferromagnetic materials because essentially they induce a temporary magnetic effect in the non-magnetized material. Essentially, they make the non-magnet a magnet, albeit only a temporary magnet, only for a short period of time. Let's take a look at the diagrams now from the activity that you just did. The first scenario in the activity you just did had a single bar magnet with a north pole and a south pole. We put the compass in various places around that magnet, and we wanted to see which way the compass needle pointed when we put it in those various spots. We're going to draw this out right now, or at least I'm going to draw it out on the board right now. We're going to see if it matches up more or less with the diagrams that you have, and then we're going to connect some dots once we've done that. We should have more or less the arrows pointing like I have them drawn here. Now, yours may not be exactly like this, but they should be relatively close to looking like this. How many people have a diagram that looks more or less like that? All right, let's start joining some dots together now. Do the old kindergarten thing where it's connect the dots. If we do that, we should see patterns that start looking like this. And I don't know if that looks familiar to you guys or not, but if you think back a month or so ago, think back to when we drew magnetic fields that surrounded individual charges and dipoles or dicharge. If we draw the field surrounding those two charges, it's going to look something like this. And hopefully that rings a bell to you. Kind of looks a little bit familiar to you. If you look at the electric field that's surrounding those two charges, that positive and negative charges, it looks an awful lot like the magnetic field that surrounds a north pole and a south pole of a magnet. This field is not this field. This is an electric field. This is a magnetic field. But the pattern surrounding those two charges looks remarkably like the pattern that surrounds those two poles. Let's do the next one. We have two magnets with a north pole and a south pole against each other. This time we should see arrows that point more or less like this. How many people have a diagram that looks something like that? Okay, let's join some dots together here now. When we do, it should look like this. That might not look familiar to you because we didn't draw something in electricity that had a pattern that looked like this, but we could. If I was to draw a positive charge and a negative charge like this, we would see the the electric field that's surrounding them would look like this. Looks like the magnetic field that's in between the North Pole and the South Pole. But if I drew another positive over here and another negative over here, we would find that the field would start looking like this, which once again starts looking remarkably like the magnetic field that surrounds these two magnets. Once again, this field is not this field. This is electric, this is magnetic, but the pattern of the two fields looks remarkably the same. Finally, we had one more diagram that you guys drew in your little activity. This time we had two magnets with north against north. The field lines should point something like this. We start joining the dots together here. What are we going to see? I don't know if that looks familiar to you or not, but start drawing some charges and see if we can make it look familiar to you. We have a positive and a positive. The field lines would go like this. looks like the magnetic field between the north and the north. We put a negative and a negative over here, we would find that the field lines start going like this. And once again, the electric field, although it's a different field than the magnetic field, looks remarkably like the magnetic field. So don't get it mixed up. Okay, don't call an electric field a magnetic field. Don't start talking about the magnetic field that surrounds a positive charge or the electric field that surrounds a pole, a north pole or a south pole. But what you can do is use the same logic that we used with electric fields and the shapes that were generated from those fields. So use the same logic for the magnetic fields. Because in the end, the shapes of the fields look the same. The shape of the field produced by a north pole and a north pole looks like the shape of the field produced by a positive and a positive. We're going to define the direction of the magnetic field now that we've drawn the diagrams. Okay, we defined the direction of the electric field in a couple of ways. We defined the direction of a gravitational field in a couple of ways. An electric field, which is a vector field, by the way, can be defined as the direction that a positive particle would move if placed in the field, also away from the positive toward the negative. The direction of the gravitational field, also a vector field, can be defined as the way that a mass would move if placed in the field, or it can be defined as toward the producer. A magnetic field is also a vector field. It can be defined, number one, is the way in which a compass needle would point if placed in the field, the north end of a compass needle. The red tip of the compass needle, the one that you guys used in the activity that you just did, the red tip is the north end. Whenever you're navigating with a compass, you're looking at the red tip of the compass, you're always looking at the north end of the compass. So the direction in which the north end of a compass, or in other words, the direction in which the compass needle would point when placed in the magnetic field. Okay, that's what we just did. We found in all those diagrams that we drew that the magnetic field pointed in the direction that the compass needle pointed. The other way that we can define the direction of the magnetic field, if the electric field was the way that a positive charge moved and from positive to negative, and a magnetic field would be the way that a compass needle points and from north to south. Again, if we go back to those diagrams that we just drew from your activity, the magnetic field in every single case went away from the north and toward the south. Away from the north and toward the south. So magnetic field is the way that a compass needle points when placed in the field, and it's also away from the north and toward the south. You guys don't have to copy it on this page. I just want to give you this page for perspective. First of all, before I go through this, I want to tell you about two quick little things. The symbol for magnetic field is a capital B with a little vector sign over it. It tells us it's a vector field. I don't know why it's not a capital M with a vector sign over it, but it isn't. Okay, magnetic field is a capital B. The symbol, or the units I should say, for magnetic field are the Tesla, or capital T. Now the table that I'm about to show you again, I said you don't have to copy down. It gives you the relative magnetic fields of different things. Okay, we want to give you a perspective. How much stronger is this magnetic field than that magnetic field? You don't have to remember any of these. You don't have to memorize any of these. I just want you to know that, oh wait, this is way stronger than this magnetic field, or this one's way weaker than that magnetic field. The Earth's magnetic field varies depending upon where you are on the surface of the Earth, but it averages about 5 times 10 to the negative 5 Tesla. It's a weak magnetic field. Just like gravity is a weak field, okay, magnetic field surrounding the Earth is a weak magnetic field. I think it's really strong, right? It affects compasses all over the place, right? No, it doesn't actually. Okay, if you're standing out in the middle of nowhere and you get a compass, it's going to point in the right direction, right? It's going to point towards the North Pole. But if all of a sudden you bring another magnet nearby, what affects the compass more? The Earth or the other magnet? What happened in the activity you guys just did? The compass should have been pointing this way, right? But when you have the magnet nearby, the compass pointed in different directions depending upon where you have the compass relative to the magnet. The magnet affected the compass way more than the Earth affected the compass. That's because the Earth's magnetic field, it's a real magnetic field and it'll affect a compass in the absence of other things, but it's still a pretty weak magnetic field relative to other things. About, give or take, 5 times 10 to the minus 5 Tesla. A typical bar magnet is about 1,000 times the strength of the Earth's magnetic field. Now, the bar magnets that you guys use in your activity have a weak magnetic field. They're weak bar magnets. But they're still way stronger than the Earth's magnetic field. And you know that because the compasses that you put around them were affected way more by those bar magnets than they were affected by the Earth's magnetic field. A sunspot, you guys have all seen pictures of sunspots, right? This solar weather that takes place on the surface of the sun, releases charged particles, generate a magnetic field that's about 10 times the strength of a bar magnet, or about 10,000 times the strength of the Earth's magnetic field. How many people have ever had an MRI for something? When you fill out a survey, you have to fill out a survey before you get an MRI, and they ask all kinds of questions, including like, you ever had metal in your eyes? And the stupidest questions you would think, the dumbest questions on the history of the Earth, right? Have you ever had metal in your eyes? Like shards of metal in your eyes? Why would they ask something like that? Well, if it's a, go ahead. Yeah, if it's a metal that's a ferromagnetic material, then it matters a lot, right? An MRI has a magnetic field of about 15 Tesla. That's a really, really strong magnetic field. That's 10 to the positive 1. Okay, that's 1,000,000 times stronger than the Earth's magnetic field. Okay, if you have some ferromagnetic material in your eye, and all of a sudden your head is inside this MRI machine with 15 Tesla magnetic field, then you risk that ferromagnetic material being pulled out of your eye, which could cause damage, obviously. If it's something like copper's not ferromagnetic, right? But if it's some kind of alloy, then there is possibly some ferromagnetic material. That's why they ask you those questions anyways, just to make sure. Yeah, I'm not sure what they do, to be honest, if you say yes. I have had shards of metal in my eye. I don't know what they do. Okay, I've only had an MRI once. They asked those questions. I got to tick off no for the answer for each of those questions. But if I had it ticked off yes, I'm not sure what they would have done. Don't know. This gives you some idea as to how strong an MRI machine is. The strongest magnet ever made by people is about 40 Tesla, only about twice the strength of an MRI machine. So MRIs are pretty strong magnets, right? If we only have the technology to generate a magnetic field that's twice that, then MRI machines are pretty strong magnets. Now this is what you don't want to get close to, especially if you got those shards of metal in your eye. A magnetic neutron star. It has a magnetic field of about, give or take a little bit, 10 to the 11 Tesla. 10 to the 16 times the strength of the Earth's magnetic field. I don't know this for a fact, but I would guess that the magnetic field surrounding a magnetic neutron star is so strong that I would guess that it would be strong enough to literally suck the iron out of your blood. Now, that doesn't sound very good. The good news is, and there is good news, long before you ever got to the magnetic neutron star, you would have died from some other source, some other cause. So you'd be dead long before you ever had to worry about the iron being sucked out of your blood. So don't worry about that, okay? It's all good. I wouldn't memorize any of these, but I would have some idea as to these numbers. Like 10 to the minus 5, 10 to the minus 2. Here's why. Not because you're going to be asked specifically what's the magnetic field strength surrounding the Earth or surrounding a bar magnet, but sometimes we calculate a value of a magnetic field and we want to know whether it's a realistic number or not. And the only way we can tell if it's realistic or not is if we have some frame of reference. We calculate the speed of a car in a collision and we get 17,000 kilometers per hour. We know we're wrong, right? Why? Because we have a frame of reference for speed. Cars are supposed to go 50, 100 kilometers per hour, right? If we calculate a magnetic field strength of 10 to the positive 17 Tesla, unless we have some frame of reference, well, then we don't know that that's not a realistic number. Make sense? So don't panic about the exact numbers, but remember that more or less, we're talking usually about 10 to the minus something for magnetic fields, but not 10 to the minus something really, really big. You know, not 10 to the minus 12, 10 to the minus 2, 10 to the minus 3, 10 to the minus 5, somewhere in that range usually would be our answer for magnetic field strength. One final thing before we wrap it up for the day. Draw a picture here of the Earth. I'm going to tie a couple things together here. The Earth generates its own magnetic field. Scientists aren't 100% positive as to how the Earth actually generates its magnetic field. We somewhat understand it. We know that it has to do with this churning magma deep within the Earth. But we don't know exactly how it happens. We don't know exactly how the Earth generates and sustains its magnetic field. We don't know exactly how the Earth changes its value of magnetic field, which it does. In the last couple hundred years, it's become about 10% weaker than it typically has been. We don't know how the Earth's magnetic field actually reverses. And geologically, that happens often. About, on average, every 250,000 years. Thanks. The Earth's magnetic field actually reverses. The poles reverse. Just so you know, we're about 500,000 years overdue for the poles reversing. And there's some scientists that actually think because it's decreased in strength by about 10% in the last couple hundred years, that we may actually be in that phase of the Earth's magnetic field reversing now. We may actually be in there. And when it happens, geological records tell us that it happens pretty quickly. So it's not like oh, okay, we got a million years before it completely reverses. We may have another couple hundred years, and it's literally reversing. We don't know that, but there's because of geological records and some indirect evidence, some scientists think that might be happening. Bottom line is, I'll ask you questions in just a second here, guys. Okay. Bottom line is the Earth does generate its own magnetic field. It's like the Earth has a bar magnet inside it. Of course it doesn't, but it's like the Earth has a bar magnet inside it. The magnetic field surrounding that bar magnet would look something like this. If we were to stand right here at the equator, a compass needle would point this way, right towards the North Pole. But wait a second. We define the direction of the magnetic field as the way that a compass needle points when placed in the field. All right, good. We also define the direction of the magnetic field as being away from the north and toward the south. So what are we saying? This is north and this is south. What I'm about to tell you is going to rock your world. What I'm about to tell you is going to go against everything that you've always believed. Not only do the penguins live way down here in Antarctica, so does Santa Claus. Because the North Pole, magnetic North Pole, is actually in Antarctica. Magnetic South Pole is Canada. We say the North Pole is Canada, right? Northern Canada. Well, geographically it is. Geographic North Pole is Canada. But magnetic North Pole isn't Canada. Magnetic South Pole is Canada. Geographic poles and magnetic poles are opposite to one another. Now, that doesn't mean if you get lost in the woods sometime with some people, you say to your friends, hey, I remember my physics teacher told me that poles are reversed, so even though the compass is saying we should go this way, we should go the opposite way. Okay, don't do that, because you'll end up deeper in the woods. Here's the deal. This is magnetic South Pole. It is. This is definitely magnetic North Pole. That's the reason you never found Santa Claus when you were a little kid, right? Because you're looking in the wrong place. It was in Antarctica, not the Arctic, not in Canada. This is truly the magnetic poles. When we're navigating, we don't call this the South Pole, we call it the North Pole. It's wrong, because magnetically it's the South Pole. But it doesn't really matter as long as we're all on the same page, right? It's really the South Pole. What do we all call it when we're navigating? The North Pole. We could call it anything we wanted, as long as we all call it the same thing, right? Call it Bob. Okay, which way are you heading? Bob. As long as we all have the same understanding as to what Bob means, then it's all good. Does that make sense? It's strictly speaking South Pole. We think of it as the North Pole, and that's okay, as long as we all think of it the same way.